My name is Blair Stratman, and as Arjun said, I'm a senior consultant at Copeland Building Envelope Consulting out of our Boston office. And today we're going to talk about what makes up an airtight building, where we typically go wrong in design and construction, and the impacts that can have on our energy efficiency and ultimately the durability and building performance. So starting with an overview, this presentation should give you a baseline understanding of airtightness, why it matters, how we design for it and build it, and then how we measure that air leakage. Whether you're an architect or consultant, hopefully you can leave here today with a few strategies for meeting modern code requirements and airtightness performance targets. So we're going to start with the fundamentals of airtightness before we talk about design strategies and construction best practices, before finishing off with the codes and standards, as well as the blower door testing and diagnostics. So to understand building airtightness, first we need to understand the air boundary. The air barrier in the building envelope is made up of building components that we typically see and some that we don't. So that's windows, and then some of our exterior wall, and then sometimes a membrane that's buried within your wall assembly. The primary function of the envelope is to shed water, control vapor and air, and then slow heat flow. Fundamentally, the envelope is made up of the roof, walls, windows and doors, and the foundation, as well as any other sort of accessory materials like gaskets or weather stripping or sealant. The building envelope serves to keep the inside in and the outside out, which keeps everybody comfortable, safe, and dry. So the building envelope is made up of 4 barriers: water, air, vapor, and thermal. The performance of any building inherently hinges on the continuity of these 4 barriers and the continued performance of the installed materials. And so today we're going to be looking at and talking about only the air barrier continuity. And looking a little more into the basic principles of air movement, airflow requires 2 things for it to flow. It requires a difference in pressure and an opening for the air to move. Air always flows from areas of high pressure to low pressure. At a higher pressure difference, your air is going to flow faster through the opening, and thus more air is going to move. And what can be so detrimental about air leakage is that air can carry whatever's in the air along with it, like water vapor. And airflow has the ability to move a lot of water very fast. If this doesn't make sense more fundamentally, the act of breathing is also airflow. So when you breathe out and you exhale, you're making the pressure inside of your lungs lower than the atmospheric pressure, which then causes air to flow in, which we call inhalation. So, looking at the fundamentals of airtightness. As buildings exist, they're all inherently pressurized. If you think about the building envelope as the skin of a building, like a bubble, there is some pressure difference between the inside of your bubble and the air outside. In order to not leak extraneous air, we have to design and build our buildings to be airtight. How we make buildings airtight is driven primarily by these baseline factors and the nature of these baseline building pressurizations. So when there's a temperature difference between the inside of the building and the outside of your building, which seasonally varies, right? In the winter, it's going to be colder outside than it is inside, and then vice versa in the winter, or maybe in Atlanta, it's still hotter outside in the winter than it is inside. A pressure difference is essentially created across the envelope due to the temperature difference. For buildings that are at least 4 stories tall, the pressure created by the temperature difference then creates a difference in pressure when we compare the top floor of the building, say, to the bottom floor, which we typically refer to as the stack effect. Wind is airflow, which then translates to dynamic energy applied to a building roof or wall, and pressures felt by the building varies, obviously, per elevation. If you're on the coast, you're going to get a lot of wind on one elevation versus the rest of them, which is going to affect how the air leakage leaks at your building. And then finally, mechanical system airflow, which is the design building pressurization. The HVAC systems are designed to control the amount of intake into your building and then the amount of exhaust. And this is designed typically where there's an intention to if the building is positively or negatively pressurized. So what is whole building air tightness? Air tightness minimizes the unwanted air leakage in or out of a building. And since we know that air moves due to pressure differences, if there's gaps in our enclosure, the air is going to find its way in or out. Air tightness promotes energy efficiency, the control of indoor air quality, as well as tenant comfort. And it also inherently prevents condensation and any unwanted pests. Air tightness differs from ventilation, as ventilation is the controlled exchange of indoor and outdoor air to maintain your indoor quality and also remove pollutants. Today we're focusing on eliminating our extraneous air leakage. So you have a building and it's not airtight. What are the risks? So generally, if there's any air leakage, uncontrolled air leakage can contribute to moisture problems that affect occupant health and your structure durability. A large amount of air leakage can also impact your indoor air quality. So heating and cooling typically accounts for the greatest energy usage in buildings, and it's estimated that air leakage can typically account for 25 to 40% of that HVAC cost. For taller buildings, that larger pressure difference at the height of the building is caused by the stack effect that amplifies the amount of air leakage, which then increases essentially your air leakage at the top of the building. So this diagram here is a tall building structure with some sort of like core or elevator shaft that's running through the building. And this is typical winter conditions where it's cold outside and warm inside. Based on the temperature difference between these two things, there's going to be a natural difference in pressure between the bottom floor and the top floor. And the air is going to be sucked in at the bottom floor and then go up through the building. There will be some neutral pressure line. We might be around there in this building. I don't know how tall this building is, but we might be somewhere around the neutral pressure line here. And then up at the top, you'd have positive pressure where the air is just flowing out and all your warm air is getting lost out to the environment. So in the summer, this graph would essentially be reversed and the air would be flowing in through the top. You'd have a negative pressure on top, and then it would be exfiltrating all of your nice air-conditioned air out to outside. So if our building's not airtight and we can't control the amount of air leaking into the building due to the pressure differences, it becomes much harder after construction to modify the mechanical systems to counteract the building pressure. But we do have some good news, or at least one way to reduce this large pressure difference between the top and the bottom of the building. Does anybody have any idea what I'm trying to lead into? Kind of. More specific to this.
Insulation.
No, not insulation.
Return air systems.
Not return air systems. Kind of. So floor to floor compartmentalization. So right, essentially making smaller air compartments. Yes, but within smaller compartments of the building, instead of having it be one bubble, you're making like 30 bubbles across the full height of the building. Yeah. So in this diagram, right, same typical winter conditions, this red box is sort of outlining, that would be like one airtight compartment. So think like apartment units or like different tenants on each floor that have their own like HVAC system. And here you get a neutral pressure axis at each floor, where then your magnitude of the overall pressure difference decreases with compartmentalization. So this is a really good design strategy that can get tricky around the core of a building and around elevator steps, but this could be an entire presentation in and of itself, and it's a difficult design strategy, but it's worthwhile in terms of your overall energy efficiency and building performance. Typically, yeah. So right, it's more common. It's becoming more common.
I don't know that I've ever had that taken into consideration in doing the uplift pressure calculations through ASCII 7 or FM.
So wind uplift, thank you for the lead-in, is an entirely different thing.
It wouldn't have any effect on it?
No, because the wind uplift as it relates to uplift pressures is due to the air flowing across the roof, which makes this sort of suction pressure, whereas the interior compartmentalization is just, right, the pressure inside of the building, which doesn't affect your values for uplift. So if your building is not tight and, right, wind runs across the roof of your building, essentially your roof membrane wants to lift up due to the suction pressure, which is why we have all of these uplift calculations for the wind loads that your roof assembly needs to be able to withstand. Here it's similarly just as important that your air barrier is also able to withstand those sort of uplift pressures. Because if the air barrier, if your roof assembly is able to move when wind runs across the top of the roof, essentially you can create a pressure difference between like the top floor and the underside of your roof assembly. And then that can drive warm air up into your roof assembly, which then in a cold climate, you're at risk of condensation forming under the roof membrane. So that said, your air barrier needs to be designed and installed to withstand the wind uplift pressures for the roof. You want your air barrier to not be able to move under the expected wind pressures. Yep.
If I add something very quickly.
Yep.
So John, to your point with interior pressurization as it relates to wind uplift, I seem to see that the interior positive pressure coefficient is like one of the considerations as you follow through all of those steps in ASC 7. Right now, it does not take into account any kind of pressure equalization from the interior. I think as it becomes more common, maybe in future code cycles, when ASC 722 doesn't have that provision. We still use ASC 716 in Europe. Who knows, maybe 2, 3 code cycles down the line, if it becomes common enough, then maybe something.
Okay, and then our last fundamental pressurization technique and what the risks are for our HVAC system airflow. The largest, first and foremost risk is the amount of money that it's going to take to power your building mechanical systems to keep your interior air conditioned the way you want it to. In airtight buildings, the energy cost and demand of the building mechanical systems is reduced. In hospitals and labs, the building is typically designed to be positively pressurized. So that means that the intake is greater than the exhaust, which keeps all of your air inside, just like fresh conditioned air from your designed intake. When a building is negatively pressurized, you risk drawing in, moisture and hot air in through deficiencies in your envelope, which can then lead to poor air quality. If you need to pressurize your building intentionally, whether positively in a hospital or lab or in a really cold climate, negatively pressurizing your building to avoid the risk of condensation, it'll be easier for you to reach your air leakage targets if your building is more airtight. So knowing the risks of non-airtight buildings, where do we typically see air leakage? It's no secret that construction deficiencies typically happen where multiple trades come together, right? So the sentiment is typically the same for air sealing. So we'll start with wall openings and penetrations, like any through wall or through roof penetrations, like this pipe penetration there, the perimeter of that's not sealed, so that's an air leakage path. And at window and door openings, transitions between adjacent wall systems like a roof to wall condition, so parapets, roof edge detailing, and wall to wall transitions like opaque wall to fenestrations. Interior compartmentalization when you do it, right? Service chases, elevator shafts, the core of the building. It can be hard because you have to air seal from your core to the underside of your roof deck at every single floor for that compartmentalization. And basements like utility corridors or any underground connection to a power plant. If you want your building to be airtight, you need to be thinking about those underground connections. So to look at design strategies, we should first look at where we typically go wrong. 2 necessary chapters happen in the book before air leakage. There's design and construction. So looking first at chapter 1, the design of the air barrier, the building code leaves a lot of room for individual discretion for the air barrier placement. So we're going to do a little air barrier exercise. Air barrier where? There are many ways to configure the air barrier continuity from the wall, the curb beneath the curtain wall sill, at the head of the curtain wall sill, transitioning to the metal panel wall above, and then from the metal panel to the roof vapor barrier. So this is sort of that condition in real life. Does anybody want to contribute where they would typically put the air barrier? It's okay if the answer is no. We're going to talk through it. Yeah, so that's one option, is providing your air barrier fully at the exterior. So you're connected here up with like a membrane and then a silicone sheet to the curtain wall, which is your air barrier, and then you connect it with membrane up to the soffit. And then your exterior soffit board is lined with the air barrier, which then connects to the roof vapor barrier. Does anybody see how this in and of itself could be risky in terms of air leakage in practical application?
The roof to water transition, maybe it's a different contractor looking at it, maybe like tie-in the fire wall.
Yep.
Yeah, well, sure, there's that. I'm trying to understand
This detail here?
yeah, it looks like you're going outboard of the insulation on the soffit and the parapet, but you're inboard of the insulation on the,
Up here?
yeah, on the wall, the vertical wall, yes, the parapet there, yeah, going up the wall, facing the parapet, you're outboard insulation on the metal panel. But when you transition from soffit to the wall, you go through the insulation here, back to what I would call the dense glass or the machine quarter.
Yep.
And then you got that rinker, by the way, that's a detail of the rinker. That's
Yeah, it is. They didn't provide it, but yeah, it is.
that one, I would, if I were doing that detail, I would pull that, you see, that's a challenging detail. Am I seeing this right? I mean, I guess there's that gap there. Okay. Oh, there we go.
So right where this could be detrimental in terms of this detailing is that here we have exterior light fixtures in the soffit. So even if we air seal around every single light fixture, most light fixtures themselves aren't intended to be airtight. So with this as it's installed, right, in a really cold climate, you're really warm inside and then you're cold outside, which drives the hot air this way, and then you get risk of condensation forming on these two surfaces. And then if it's hot outside and cold inside, then you're essentially sending hot air in through your light fixtures up to the inside, which is decreasing the efficiency of your building mechanical systems. So fully on the outside, not the most practical, doesn't look great. Other than the outside, the other option would be inside. There we go. Right. Not a hard question. Thank you. Okay, so here we're following the same line inside of the curtain wall, and then here we're considering the interior plane to be the air barrier, where air barrier is following the line of the interior drywall. And the building code does say that drywall that's a minimum of ½ inch thick counts as an air barrier. So in this application or iteration of the air barrier, does anyone see where this could go wrong in terms of air tightness?
Transition from the interior wall to the exterior glazing system.
Yep. Yeah, so if you had electrical shades here, right, then you're putting a hole straight through your air barrier on the inside. If you have electrical inside, you need to air seal around every single electrical box, right? So this,
Vapor
Right,
Paper drop cost compensation back there inside of the wall cabinet.
right, depending on where we are. Yeah. So here, I would honestly think that this condition, I mean, it looks great as designed right here, right? It's a straight line right up and through, it looks great. But here, you're probably gonna have more interior wall and ceiling penetrations than you would, right? Like that's gonna compromise your air barrier in this condition way more than it is if you had your air barrier fully on the outside. So ultimately, where did we end up with the design for this? Because fully inside gives us a lot of air leakage, and fully outside makes our soffit conditioned, and then we're at risk of condensation at the light fixtures. So if the architect wants to keep the light fixtures, where's the best place to put our air barrier? And what we ultimately ended up doing is having the air barrier follow the same plane up along this way, and then following the vertical line behind the metal panels and the wall. And then we essentially detailed the wall membrane being sealed to the underside of the roof deck. So the lower flutes were filled with spray foam, and then they put a blank off piece of metal bed and sealant and then screwed it up through the metal roof deck. And then we adhered the wall air barrier membrane to that, which then gives us that continuity while leaving the soffit unconditioned. Anybody have any questions on this sort of thing before we talk more about design?
Did the rubber flute block cause any fire problems?
Building's still being constructed, so don't know. Couldn't tell you. I wouldn't think so, right? Because like we have mineral wool up here, and then mineral wool at the extent of your soffit, and this detail is occurring probably like 3 feet or more inboard of that. Good question, though.
As long as the contractor knows that value engineer a way you're adhered assembly to a mechanically attached assembly.
True.
That would cause a lot more penetration.
Yeah. Or I think that would change the air barrier from being the roof vapor barrier to being essentially the roof membrane itself.
Yeah.
So when we talk about a building's airtightness, the most important thing to note is that it's a system that's designed for continuity by architects and engineers. It's not just one material, but a system that incorporates several different components to give us a continuous air barrier, like windows, and then your typical accessory materials like sealants or sheet applied membranes. Is everyone here who does design familiar with the pen check? Does anyone not know what the pen check is? Okay, perfect. So when you're designing the air barrier, or if you're developing any of the 4 barriers, when you have your details out on a sheet of paper, in order to check for continuity, right, you should be able to theoretically put your pen down on a piece of paper, trace over every single detail, connecting your air barrier in all of those details. And if you have to pick your pen up at any point, then you have discontinuity in your air barrier. So in order to get air tightness, especially in design, we need to think beyond the pen check and also think in 3D where these sections meet. Everybody benefits when architects explicitly describe the intent of the air barrier in the specifications. Within the air barrier specs, I would start by incorporating a description of the systems that make up the air barrier. So if the fireproofing between floor levels is intended to be the air barrier between 2 floor levels, it would be beneficial to include that information. Where possible, also specifying specific materials for the air barrier can help not only to streamline your submittal process, but also to help further communicate your design intent. And the air barrier specification should also outline the expectations for routine or final air barrier inspections, any required project mock-ups, or any intermediate air barrier testing like membrane adhesion testing or pull-off testing for, say, like a fluid-applied wall coating. The more specific these specifications are, the better, and that includes listing performance requirements or any allowable air leakage requirements in the applicable testing standards. So in Georgia, as of today, I say that because I'm not from here, The building code does not require whole building airtightness testing, but in most jurisdictions, it is listed in the building code as one option to show code compliance for your building air barrier. And in order for a testing agency or an engineer to perform the airtightness testing, they need to know the target air leakage rate and also what test standards and method to test underneath. After we discuss Chapter 2, construction, we'll look more into the various building codes and other jurisdictions that give us target air leakage rates. So within the blower door, or I guess within the air barrier specifications, where whole building air tightness testing is either elected by the project team for better construction, or if it's required by the building code. Totally lost my train of thought. Where was I going with that one? This is your list of items, essentially, to include there. So any qualifications for the testing agency, contractor responsibilities, like does the general contractor need to be there on the day of the testing? Does the architect want to be informed before the test happens so that they can make sure that they're there? The desired test method, the boundary of the test enclosures. The parentheses here would be for compartmentalizations where you have two independent air barrier enclosures. Target air tightness for your test enclosure. Conditions that have to be met before your test. So all of the windows and exterior doors and any roof penetrations need to be installed before the test, as well as the test reporting criteria and language on how the test result is reported, including like confidence intervals, pass-fail criteria, and also the remedial process in case of a failing test where you get more air leakage than is specified allowable. So that's it for design. Looking at Chapter 2, construction, the implementation of the air barrier design and what best practices look like. So as a contractor, when preparing to bid and deliver on an airtight building, what do you need to be prepared for? Those guys like to talk in phases, so I put it in phases. Pre-construction, we need to plan. During construction, we need to monitor. And then during and post-construction, we need to evaluate the air barrier. So pre-construction, look for the air barrier criteria, understanding how it's defined and how any test criteria is defined and what materials are specified. After we know what the pass-fail criteria is, what are the specific components of the air barrier? Right? Are there missing components that weren't specified? And is the air barrier design delegated, maybe by omission, to the general contractor? During construction, are there any QA/QC requirements or any air barrier auditing requirements? To construct an airtight building, the contractor needs to understand and put materials to building components, if not already done so by the specifications, while thinking proactively, of course, about material compatibility, constructability, and installation sequencing as it relates to compatibility. And the last big one that catches everyone off guard, especially when a whole building air tightness test is scheduled, is scheduling. When does the test need to happen and what's the impact on your schedule? When you perform a whole building air tightness test, essentially all of your boundary needs to be controlled. So that means all of your exterior doors need to be closed and locked. So in an occupied building, this typically means the testing happens on the weekends when people aren't there trying to go in and out of the building. Or in new construction, it typically happens either on the weekends or after hours when everybody else on the site has left for the day and only like the lucky few are there to get to see the test. So the two most important questions before construction is complete that we need to answer is who's responsible for integrating the air barrier materials and who's undertaking the risk and responsibility for it, maybe without knowing. So after construction best practices, when it comes time to construct your building, what gives? The first big things that can lead to air leakage while installing your building air barrier is installation sequencing and workmanship. The picture on the right here is a new addition building roof, and this is the backside of the plywood sheathing that's running perpendicular into the existing building wall. In this picture, there's a minimum of 2, maybe 4 installers who are involved in making this detail airtight. As you can see, the wall membrane installer did his job, kind of, and installed the wall membrane up to here within the general vicinity of the corner. The mason installed his self-adhering air barrier membrane below the new flashing, and then the roof vapor barrier is also installed on the concrete roof deck, and the building expansion joint, the compressible filler, is here. And the way this detail was designed is that all of these materials come together and essentially die into this compressible joint, which would then make this corner airtight. So in this instance, the roof air barrier, or the roof vapor barrier, is acting as our air barrier. And so as this is constructed, right, we don't know who came first. We don't know who did what. So there's no real way for us to point any fingers and say this person didn't do what they were supposed to do. All we know is that this condition, as it's installed, once the roof membrane is put over it over time, if it's cold outside, right, then we're going to get warm air that permeates up through this joint between the compressible filler and the plywood, and also through any fasteners in the back of the plywood that would essentially create a buildup of moisture in this interior corner condition that's concealed under the roof membrane. So to correct, or condensation here is, right, condensation is going to happen. It's going to be much more exacerbated if it's cold outside and you have like a hot interior climate inside, like a natatorium. This would be like detrimental there. And similarly, in a hot exterior climate, if you're really air conditioned inside, you might see the same sort of thing. So to correct this condition, the roof vapor barrier should have been extended horizontally to then die into the compressible filler, and the wall membranes too would have been brought down so that they terminated below where this compressible filler is to give us that air barrier continuity. So now looking at the codes and standards that outline what is too much air leakage and the proper way to perform airtightness testing. So the basis of air leakage testing or whole building airtightness testing is typically getting your passing value for your air leakage rate. Everyone wants to know what's too much and how to avoid exceeding it. So here's a few typical notations when people talk about airtightness. So ACH 50 stands for air changes per hour at 50 pascals of pressure, which is 0.2 inches water column, if that's the pressure that you know instead. It's a metric for airtightness in terms of air exchange. So it tells you how many times the air volume inside is replaced with air from outside per hour when the building is under a pressure of 50 pascals. CFM 50 is the more common metric, which refers to the airflow in cubic feet per minute. When the building is under pressure of 50 pascals, you could also see CFM 75, which would mean the same thing, just at a pressure of 75 pascals. And this gives you a more instantaneous airflow measurement at some pressure. And here for ACH 50 and CFM 50, a lower value means your building is more airtight. And then building codes and standards specify the maximum air leakage thresholds, and the tests need to follow the protocols set forth by those standard test methods, which leads us to ASTM E779, whose official name is Standard Test Method for Determining Air Leakage Rates by Fan Pressurization. And that's exactly what it is. It's using fans to pressurize and depressurize your building using controlled fan airflow. So by introducing a known amount of airflow into or out of your building envelope, the pressure difference that we induce with that, or lack thereof, with a whole bunch of computing, then turns out to be some air leakage value for a known envelope area. And this test method helps us to actually get a number and measure the building's air leakage, which helps us to assess the building's airtightness by comparing it to industry standards of what good air tightness is, as well as helping us to identify specific areas in the building where there is active infiltration or exfiltration. So the industry standard recommendations for air tightness, here's a whole bunch of them for pass-fail criteria, a few for designers to choose from, including the Energy Conservation Code, International Energy Conservation Code, honorary mention to the Massachusetts Stretch Code, and then the U.S. Army Corps of Engineers and Passive House standards. Of course, complying with any of one of these jurisdictions has different unrelated implications, but it's nice to see the range of acceptable air leakage criteria as we continue to trend towards more stringent air tightness in our buildings. So earlier I said that fan testing gives us a value for air leakage for some known envelope area. To get an air leakage rate, we have to know the envelope area. So for each air tightness test, either one person or a group of people are doing a envelope area calculation, which is the air barrier area at the roof, at the floor slab, and then the area of your above and below grade walls. So it helps us that we also get the below grade, because there's not much air leakage right between like a concrete basement and any backfill, but you get that envelope area. The envelope area is a little bit different when you're doing compartmentalized, but essentially it's the same, super simplified. It's all 6 sides of the box. It's not floor area, it's not roof area, but it's the entire bubble of your air barrier. The resultant envelope area, which is agreed upon by the designers and the engineers, can then be multiplied by your minimum allowable air leakage rate, which then gives you a total value for allowable air leakage. So what does this all mean for Georgia? Nothing today, nothing today. As of today, Georgia is following the state minimum standard building code with 2018 IBC amendments and the minimum state energy code 2015 with IECC amendments. And the IBC is very specific in stating that continuous air barrier shall be provided throughout the building thermal envelope. And then it goes on to say that it can be provided at the outside or the inside of the wall. It can be different materials that come together. It can be something buried within the assembly or any combination thereof. So currently there's no requirements for whole building air tightness testing, but I wouldn't be surprised if it came up in the next 1 or 2 code iterations. And then in researching the code in Georgia, I just found this as an interesting aside, and I wanted to share because I'm not from here, but residentially in 13 counties surrounding Atlanta, they recently adopted a local amendment that new construction 1 to 2 family homes in these climate zones need to test and pass an ASTM E779 test at an air leakage rate of less than 5 air change per hour at 50 pascals. So that is a much higher allowable air leakage rate than any sort of commercial air leakage rate. But if you're from any of these counties and you're planning on building a home in the next 45 years, maybe you'll see a blower door test. So now actually talking about blower door testing. Blower door testing as described in ASTM E779 is using fans within a door opening to induce a building pressure to measure an amount of air leakage through your building envelope. The test procedure starts with preparing your envelope on the day of testing, so closing all of your windows and doors and making sure if you have any operable windows, the tenants aren't opening the windows while the testing is being done. Your building mechanical systems also have to be shut off. After the blower door fans are installed, we do pressure testing to get an air leakage measurement in both directions, positively and negatively, pressurizing the building, and then with that fan pressure induced, we can then do additional diagnostic testing or investigation to pinpoint large or repetitive areas of air leakage. So to prepare the envelope, all the windows and doors are closed, and then you typically tape off and seal all these intentional air moving openings like a louver within an air handling unit, because here, the point of this test, right, is to measure the amount of extraneous air leakage through our envelope. So by taping these off, we're essentially excluding the leakage through our louvers which are designed and intended to move air. So we collect periods of data to get an average building pressure at some average airflow with the fans. And then once we collect data in one direction, we flip the fans around and then do the same thing in the opposite direction. So here's a little snippet of if you were to observe a whole building airtightness test, this is sort of what the computer software looks like. The dashed green rectangles are the baseline building pressure where the doors are just closed, and the little blips that you see is typically just like air movement. So here the x-axis is time and the y-axis is building pressure. And this is for a negative pressure test. So here you can see that the building baseline pressure is a little bit lower, like is operating already in the negatives. And then you incrementally use the fans to step down the pressure in controlled increments to then we collect these periods of data. So each green rectangle is like a 30-second period of time, which then essentially each green rectangle spits us out one data point for an average airflow at some pressure. So what are we looking for in a test report other than the word pass? This is one of the two graphs that you'll get in your report, right? So each one of these green rectangles then correlates to a data point that winds up on this dashed line. This line follows the equation for airflow, which is Q is the total airflow, C is some air leakage coefficient, which if it's higher, your building is more leaky. Delta P is the difference in pressure, and then N is your unitless airflow exponent. And here, the graph shows your envelope pressure between 0 and 80, and then on the y-axis, you have your building air leakage in cubic feet per minute. And so here they're reporting at 75 pascals, which is the blue dot, the blue dash line. And then each of these dots, right, typically falls along this line. And when this is reported, I guess you get a correlation coefficient, which is essentially the R-squared value, which tells you how in line with the anticipated air leakage that your measurements are. Because right, when we're performing this test out in the field, obviously wind is moving around and we don't have like a perfect bubble around the bubble that we're trying to test. So we're gonna have some variability or like confidence intervals. But you want all of these dots to essentially fall on this line. And what's cool about doing this test is when you're sitting at the computer and you're manipulating the pressure on the computer, if you pull a data point and then you move the pressure up and then you take another data point, if let's say a temporary seal, so let's say you're doing this test and one of your doors didn't arrive on site. So instead of having a door in the opening, they put polyiso in the opening and they taped the seams of that. If we're pressurizing the building and for some reason some of that tape popped off and there was an increase in air leakage, you would see the data points show up like way up here and not in line with the graph at all. And so in that way, you can tell on the computer with your graph if any of your building envelope conditions have changed while you're doing the testing. Okay. So now we know at least a little bit about conducting blower door testing. So you know how much air is leaking into your building, and you want to find out where your air is coming from, or you're just looking at your building envelope and you're not sure if it's airtight. One of the best diagnostic tools, especially during construction, is tools that a lot of us are already equipped with, looking and feeling. So your hand, if there is a pressure difference between the inside of the building and the outside, if you put your hand up to like the perimeter of a door frame, your hand would be able to feel that like air flowing across it in the same way that you might feel cold around like standing near a drafty window, an old window. So tangentially to that, test often. Test your mock-ups, require window performance testing, and then maybe even require compartmentalization and compartmentalization testing. The typical diagnostic tools that we use in conjunction with the ASTM E779 are those listed in this other ASTM standard E1186. More formerly known as Standard Practices for Air Leakage Site Detection in Building Envelopes and Air Barrier Systems, to reveal air leakage pathways that typically aren't visible to us. So we can use infrared thermography, also known as thermal scanning, also known as IR camera, and tracer smoke. An IR camera would be, you can use a handheld camera or a drone, and then tracer smoke, you can use some sort of smoke pencil or a theatrical fog machine. And so here, this is a picture of fog moving through open joints in a CMU block wall during a compartmentalized test. So this is essentially like a side core of the building where this should have been sealed to the other side of the roof deck, and we're getting air leakage through where it should have been sealed. And fog testing, if you're inside of a building that's being positively pressurized, if you apply smoke somewhere where you think there's air leakage, the smoke will just get sucked into the wall, and then you know that in some way the air is able to move through your enclosure. And then if you're depressurized, you can have somebody outside applying fog and have somebody inside. And if the person inside sees the fog, right, if the fog comes through the wall, we know that we found another breach in the air barrier. And then interpreting IR images can be hard to discern, as the temperature difference seen in the picture can be attributed to either air leakage or thermal bridging. And so the way that we discern between these two and understand if this is a thermal bridge or an air barrier deficiency is by having essentially two identical IR images, which I don't have here today, but one is when the building is positively pressurized, and the other one is when your building is at a baseline, just operating as it is. If when you compare those two pictures, if in the pressurized scan your warm spot's bigger, right, then you know that essentially now there's more warm air flowing out through here. So thermal bridging can be ruled out, and we can attribute that sort of deficiency to air leakage. So what does this thermal image get us? What does it mean? How is it helpful? And what does this mean at areas where there's uncharacteristic air leakage? So this is a building soffit with, what you can't see in this picture is there's a security camera up in this corner here. But we were lucky enough here that because it was written into the specs, that anywhere we had any sort of ambiguous results for the air leakage testing, that the contractor was responsible for conducting exploratory openings at these locations. So after our test, the contractor went back and made an opening in the soffit where we saw this air leakage. Does anybody want to guess what we found? Oh yeah. So someone had come to wire either the security camera or a light fixture, and they essentially just punched a hole through the exterior sheathing, which has the air barrier applied on it. Maybe that mineral wool was already there. Maybe they just packed it into the opening saying it was all well and fine, but somewhere where it's really cold, in this case, if this building was a museum, so if your building is positively pressurized, especially when it's cold, here, if it's really extreme, you get moisture collecting, and especially this mineral wool could hold a lot of water, and in that way, you might, in the winter, see icicles actually like forming at the outside of the security cameras or the light fixtures.
Was there a detail for that conduit at the time? Or was that delegated to the security contractor?
I believe that would be a security contractor, right? So this would have like a typical architectural detail for the rising wall, and then maybe the soffit coming into the rising wall, which shows the air barrier here and then continuing along this way. But right where we typically run into issues is where after all of that's said and done and everyone says this looks good, then the soffit is enclosed with some sort of trim, and then someone comes back and says, I need to install the security camera, I need to make an opening in this wall. Right, and the general contractor is like, okay, go make the opening in the wall, and then when we don't go back and check, this is what happens. And so this condition here is essentially, for the lifetime of the building, is just dollars that are walking out the door in a condition that we can't see. So, to sum it all up, airtightness is critical for building performance. It has to be designed, built, and tested, for lack of better words, with intention. So we do that by integrating strategies early and consistently, requiring good quality assurance and quality control programs, and verifying the quality of construction. We can specify air tightness and measure building or individual component air leakiness to increase the overall quality and durability of our final construction product. Prioritizing well-designed and properly installed air barrier systems helps our project teams to deliver cost-effective, sustainable buildings that perform efficiently for many years. Thank you.
Very good.